Subscribe to the channel so you don't miss out on any of these videos. Imagine a cosmic engine so powerful that it lights up the darkness of the universe, outshining entire galaxies. Now, picture this engine slowly burning out, transitioning into something much quieter, almost unnoticeable in the vast expanse of space. What happens when the brightest beacons in the cosmos, quasars, dim and transform into something else entirely? The life cycle of quasars and their evolution into passive galaxies is one of the greatest unsolved mysteries of space, raising questions about the forces that govern the cosmos and our place within it. What causes this transformation? And what can these cosmic relics tell us about the future of our own galaxy? To understand this fascinating phenomenon, we must first unravel the enigmatic nature of quasars themselves. These celestial objects are not stars but the blazing centers of galaxies where supermassive black holes devour matter at an incredible rate. This process releases an immense amount of energy, creating a dazzling beacon visible across billions of light years. But quasars are not eternal. Like everything in the universe, they have a life cycle, and their transformation into passive galaxies, a process that seems almost anticlimactic, hints at the ever-changing dynamics of space. At the heart of every quasar lies a supermassive black hole, a gravitational monster millions to billions of times the mass of our Sun. These black holes are surrounded by a swirling disk of gas, dust, and other material. As this material spirals inward, it heats up due to friction and gravitational forces, emitting light across the entire electromagnetic spectrum. This is what makes quasars so bright and detectable even from the furthest reaches of the universe. Yet, their immense energy output is both a blessing and a curse. Over time, the very activity that powers them begins to sow the seeds of their quiet demise. Quasars are most commonly observed in the early universe, peaking in activity about 10 billion years ago. This timing is no coincidence. The early universe was a chaotic place, with galaxies frequently colliding and merging, creating the perfect conditions for quasars to ignite. These collisions funneled vast amounts of gas and dust into the centers of galaxies, feeding their central black holes and triggering the explosive quasar phase. During this period, quasars acted like cosmic lighthouses, illuminating the distant universe and offering a glimpse into its turbulent infancy. But why don't quasars last forever? The answer lies in their appetite. As a quasar consumes the material around it, it begins to run out of fuel. Without a steady supply of gas and dust, the black hole can no longer sustain its intense activity. Additionally, the radiation and powerful winds emitted by quasars can blow away the very material they rely on, cutting off their own supply lines. This feedback mechanism, known as quasar feedback, plays a crucial role in regulating star formation and shaping the evolution of galaxies. As the quasar phase winds down, the once active galaxy enters a quieter phase, transitioning into what astronomers call a passive galaxy. These galaxies are often elliptical in shape, with little to no ongoing star formation. The supermassive black hole at the center, while still present, becomes dormant, no longer accreting material or emitting significant radiation. This transformation marks the end of an era, but it also raises new questions. Why do some galaxies become passive while others remain active? What role do environmental factors, such as the galaxy's location in a cluster or its interactions with neighboring galaxies, play in this process? One theory suggests that the size and mass of the galaxy's central black hole are key factors. Observations show that larger black holes tend to shut down their host galaxies more effectively, perhaps because they generate stronger feedback mechanisms. Another possibility is that the surrounding environment determines a galaxy's fate. Galaxies in dense clusters may experience gravitational interactions that strip them of their gas, accelerating their transition into a passive state. Alternatively, the availability of cold gas, the raw material for both star formation and black hole accretion, might be the ultimate deciding factor. Interestingly, this process has implications for our own Milky Way galaxy. Although the Milky Way is not currently a quasar, it harbors a supermassive black hole at its center known as Sagittarius A star. Could it have been a quasar in the distant past? And could it one day evolve into a passive galaxy? While the Milky Way is still actively forming stars, Its future depends on a delicate balance of forces. Understanding the life cycle of quasars could provide critical insights into the long-term fate of our own galaxy and its neighbors. The study of quasars and their transformation into passive galaxies also sheds light on the broader history of the universe. By observing quasars at different distances, astronomers can essentially look back in time, piecing together a timeline of cosmic evolution. These observations reveal that quasars were far more common in the early universe, reflecting an era of rapid growth and transformation. Over time, as the universe expanded and cooled, the frequency of quasars declined, giving way to a quieter, more settled cosmos. Yet, despite decades of research, many mysteries remain. For instance, some quasars appear to reignite after long periods of dormancy, suggesting that their life cycle might be more complex than previously thought. What causes this resurgence? Is it the result of a new influx of material, perhaps triggered by a galactic merger? Or are there other, as yet unknown processes at play? These questions keep astronomers on the edge of discovery, using ever more advanced telescopes and simulations to probe the nature of these cosmic giants. The story of quasars is a story of extremes, of immense energy, violent transformations, and the relentless march of time. It's a reminder of the dynamic, ever-changing nature of the universe, where even the brightest lights eventually fade. But their legacy endures, written in the structure and composition of the galaxies they leave behind. Through the study of quasars, we gain not only a deeper understanding of the cosmos but also a sense of our own place in this vast, interconnected tapestry. But this tapestry of quasars and their evolution isn't just about the visible light they emit, or the powerful black holes they harbor. It's also about the ripple effects they create across cosmic scales. When a quasar flares into existence, it doesn't just illuminate its surroundings. It fundamentally alters the structure and evolution of its host galaxy and the space beyond. To truly grasp how quasars transition into passive galaxies, we need to delve deeper into the profound ways they shape their environments. One of the most significant ways quasars influence their surroundings is through their powerful outflows, also known as quasar winds. These winds, driven by the energy released during the accretion process, can reach velocities of thousands of kilometers per second. Imagine a gale so strong it could sweep away an entire galaxy's worth of gas. These winds carry massive amounts of energy and material, dispersing it across vast regions of space. While this might sound destructive, it serves an essential purpose in the life cycle of a galaxy. By expelling gas and dust, quasar winds can suppress star formation within the host galaxy. Without these building blocks, new stars can't form, effectively halting the galaxy's growth. This process, often referred to as feedback, is thought to play a critical role in the transition from an active quasar phase to a passive galaxy phase. In some cases, this feedback can be so extreme that it ejects material far beyond the galaxy itself, enriching the intergalactic medium with heavy elements forged in stars. This means that quasars, despite their seemingly destructive nature, contribute to the cosmic recycling process, seeding future generations of galaxies and stars. But the story doesn't end there. Quasars also interact with their host galaxies on more subtle levels, influencing their structure and dynamics. Observations show that galaxies hosting quasars often display peculiar features, such as tidal tails or irregular shapes, hinting at past interactions or mergers. These mergers likely played a pivotal role in triggering the quasar phase by funneling gas toward the central black hole. Yet, they also leave behind lasting imprints, sculpting the galaxy into its final, passive form. This evolutionary journey is not uniform. It varies greatly depending on the quasar's environment and host galaxy. For instance, quasars in denser environments, such as galaxy clusters, may experience different evolutionary paths compared to those in isolation. In clusters, gravitational interactions with neighboring galaxies can strip away material, hastening the quasar's decline and accelerating the galaxy's transition to passivity. Conversely, isolated quasars might have more prolonged lifespans, feeding off a steady but limited supply of material until they too fade into dormancy. One of the most compelling mysteries in this field is understanding why some quasars seem to defy the odds, remaining active far longer than expected. These so-called Radio-loud quasars emit not only intense light but also powerful jets of radio waves, extending for millions of light years. These jets, composed of highly energetic particles, are launched from the regions near the black hole, guided by magnetic fields. Unlike their radio-quiet counterparts, these quasars appear to maintain their activity for billions of years. Why do they persist? And what role do these jets play in shaping their host galaxies and beyond? The answers to these questions may lie in the black holes themselves. Recent studies suggest that the spin of a black hole, a measure of how quickly it rotates, could be a critical factor. Faster spinning black holes might generate stronger magnetic fields, enabling the formation of more powerful jets. This, in turn, could sustain the quasar phase for longer periods. Alternatively, the properties of the surrounding accretion disk, or the galaxy's initial conditions, might play a role, creating a complex interplay of factors that govern the quasar's life cycle. As quasars transition into passive galaxies, they leave behind remnants that are anything but inert. The supermassive black hole at the center, though no longer accreting material at the same rate, remains a dominant force. These dormant black holes continue to influence their host galaxies, shaping their dynamics and even their long-term evolution. Observations of nearby elliptical galaxies, many of which are thought to be the end states of quasar-hosting galaxies, reveal signs of past quasar activity in the form of faint radio emissions or residual hot gas. Furthermore, these galaxies often serve as cosmic archives, preserving the history of their more tumultuous past. By studying their structure, composition, and motion, astronomers can piece together the story of their quasar phase and the transitions that followed. This forensic approach has led to surprising discoveries, such as the realization that many passive galaxies harbor faint but detectable rings of gas and dust, potentially remnants of their quasar winds. But perhaps the most intriguing aspect of this transformation is its connection to dark matter, the invisible, mysterious substance that makes up a significant portion of the universe's mass. Recent simulations suggest that the distribution of dark matter within a galaxy can influence its evolution, including its transition from a quasar to a passive galaxy. For instance, galaxies with more concentrated dark matter halos might retain their gas longer, delaying the quasar's decline. Conversely, galaxies with less dark matter might lose their material more quickly, accelerating their transformation. This interplay between quasars, galaxies, and dark matter highlights the interconnected nature of cosmic evolution. Quasars, once thought to be isolated phenomena, are now understood to be integral players in the larger story of the universe. Their life cycles mirror the universe's own journey, from a hot, dense beginning to a quieter, more stable present. And yet they also remind us that the cosmos is far from static. Even in their dormancy, passive galaxies carry the echoes of their quasar past, a testament to the dynamic, ever-changing nature of the universe. As our telescopes become more advanced and our simulations more precise, the mysteries of quasars and their evolution continue to unfold. But for every answer we uncover, new questions emerge, keeping the story alive and compelling. What other secrets do these cosmic giants hold? How do they fit into the larger puzzle of cosmic evolution? And what can they teach us about the ultimate fate of the universe? Quasars and their eventual transformation into passive galaxies not only shed light on the evolutionary processes of individual systems, but also offer critical insights into the universe's grand design. They challenge us to question how energy, matter, and time interweave to shape the cosmos. The more we learn about quasars, the more they reveal themselves as cosmic architects, both creators and destroyers, sculpting galaxies and influencing the intergalactic medium in ways we are just beginning to understand. For instance, the interaction between quasar winds and the surrounding intergalactic medium creates immense shock waves that ripple through space, heating gas and scattering heavier elements like carbon and oxygen. These shock waves can travel hundreds of thousands of light years, enriching regions far from the host galaxy. This enrichment process lays the groundwork for future star formation in neighboring galaxies or even entire galaxy clusters. Without quasars, the chemical diversity of the universe might look very different. They act as catalysts for cosmic chemistry, ensuring that life-enabling elements are spread across vast regions of space. But while quasars seem to be agents of change on such grand scales, they also embody profound enigmas. For example, their light, which often takes billions of years to reach us, acts as a time machine, allowing astronomers to peer into the universe's distant past. Yet this light doesn't just illuminate the quasar itself, it also interacts with the intervening material. By analyzing the absorption lines in quasar spectra, scientists can study the composition and behavior of ancient gas clouds, tracing the early stages of cosmic evolution. Through quasars, we can understand the universe as it was billions of years ago, its density, temperature, and even the rate at which galaxies were forming. One of the more recent breakthroughs in quasar research involves their role in mapping the distribution of dark energy, the mysterious force driving the universe's accelerated expansion. By studying the positions and movements of quasars over time, astronomers can trace the universe's expansion history and refine our understanding of dark energy's effects. This is an area of active research, as the data from quasars could unlock some of the deepest secrets about the universe's fate. Will it continue to expand forever? Will it slow down and collapse? Or is something even more exotic at play? Quasars are also central to solving one of the most puzzling questions in astrophysics. How do supermassive black holes grow so quickly in the early universe? Observations have revealed quasars that existed when the universe was less than 1 billion years old. These early quasars harbor black holes with masses equivalent to billions of suns, defying conventional growth models. Theories have been proposed, ranging from the collapse of massive primordial gas clouds to mergers of smaller black holes. However, none fully explain the rapid formation of these cosmic behemoths. This remains a tantalizing mystery that could reshape our understanding of the early universe. Another intriguing avenue of research is the connection between quasars and cosmic reionization, a period when the first galaxies and quasars flooded the universe with ultraviolet light, reionizing neutral hydrogen atoms. Quasars, with their intense radiation, likely played a significant role in this epoch, altering the state of the universe and paving the way for the structures we see today. By studying quasars from this era, astronomers hope to piece together the final stages of the universe's dark ages, a time before stars and galaxies lit up the cosmos. The diversity of quasars also complicates their story. While the most luminous quasars dominate the narrative, there exists a population of fainter, less active quasars that could hold the key to understanding their full life cycle. These low-luminosity quasars might represent a transitional phase, bridging the gap between the most active quasars and the passive galaxies they become. Identifying and studying these quieter quasars could provide invaluable insights into how their activity winds down and what determines the timescale of their decline. Observations of the surrounding environments of quasars further deepen their story. For instance, the cosmic web, the vast, filamentary structure of galaxies and gas that stretches across the universe, often appears intertwined with quasar activity. Many quasars are located at the intersections of these filaments, where gas density is highest. This positioning suggests that the large-scale structure of the universe might play a role in both triggering and sustaining quasar activity. Conversely, quasars, through their energetic winds and radiation, might influence the evolution of the cosmic web itself, shaping the distribution of galaxies and matter. As quasars fade and their host galaxies transition to passivity, the galaxies often exhibit remarkable stability. Elliptical galaxies, which are thought to be the remnants of quasar hosts, appear to have exhausted most of their star-forming material. However, their stars are tightly packed and exhibit little rotational motion, a stark contrast to the spiral arms of younger, star-forming galaxies. This structural rigidity hints at the violent past these galaxies endured, mergers, outflows, and the intense radiation of their quasar phase. Yet, even as passive galaxies, these systems are not entirely lifeless. Observations show that some elliptical galaxies still harbor low levels of star formation, fueled by residual gas or material acquired through minor mergers with smaller galaxies. These rejuvenated galaxies demonstrate that the transition from a quasar to a passive galaxy is not always final. The cosmos, it seems, resists clear boundaries, with cycles of activity and dormancy playing out over billions of years. Quasars also hold implications for understanding time itself. Because their light travels such immense distances, quasars enable astronomers to measure the universe's age and the rate of its expansion. They act as distant signposts, allowing scientists to calibrate cosmic distances and refine models of the universe's history. This role makes quasars invaluable not only for studying galaxies but also for probing the fundamental nature of reality. Despite all we've uncovered, quasars remain full of surprises. Each new observation seems to challenge our understanding, pushing the boundaries of what we thought was possible. They remind us that the universe is not a static entity but a dynamic, ever-changing arena of cosmic forces. The story of quasars and their evolution into passive galaxies is far from over. It's a narrative that continues to unfold, revealing new chapters with every technological advance and every discovery. And perhaps the greatest mystery of all is what quasars can tell us about ourselves. In their brilliance, we see the echoes of creation, the relentless drive toward complexity, and the cycles of activity and rest that define not just galaxies but life itself. Quasars are more than distant beacons of light. They are cosmic storytellers, bearing witness to the universe's past and pointing toward its future. The cosmic role of quasars extends far beyond their immediate vicinity, and their transformation into passive galaxies continues to provoke deep questions about the life cycle of the universe. As they fade, quasars leave behind a legacy imprinted in the structures, compositions, and dynamics of galaxies. Their influence, though no longer marked by intense radiation, persists as a quieter but no less significant presence. This transition from chaos to order, from the high-energy storm of a quasar to the serene stability of a mature galaxy, mirrors the broader evolution of the universe itself. One particularly fascinating area of study concerns how the death of a quasar affects its host galaxy's morphology. Active quasars often reside in galaxies with irregular, chaotic structures, likely due to galaxy mergers that fuel their activity. But as the quasar dims, the turbulence subsides, and the galaxy settles into a more orderly form. Observations suggest that many former quasar hosts transition into elliptical galaxies, which are smooth, spheroidal, and devoid of significant internal motion. This process raises intriguing questions. Does the quasar's activity directly sculpt the galaxy's final shape? Or does the shape emerge naturally as the turbulence of the quasar phase dissipates? This transformation is not uniform across all quasars, as the environment plays a crucial role. Quasars situated in dense clusters of galaxies, for example, might experience prolonged activity due to frequent interactions with nearby galaxies. These interactions can funnel fresh material into the central black hole, reigniting quasar activity. In such cases, the life cycle of a quasar may not follow a straightforward path from activity to passivity, but instead oscillate between phases of dormancy and reactivation. These zombie quasars, as some astronomers call them, defy the traditional understanding of galactic evolution, demonstrating the diversity of pathways galaxies can take. Additionally, the end of a quasar's active phase doesn't necessarily mark the end of its black hole's influence. The supermassive black holes that powered these luminous beacons remain at the cores of their galaxies, continuing to exert gravitational control. Even without an active accretion disk, these black holes can disrupt their surroundings through gravitational interactions and the emission of weak, relativistic jets. This quiet influence often shapes the distribution of stars and gas in the host galaxy, creating structures such as elongated stellar streams or low-density voids in the interstellar medium. The quiet phase of a galaxy also offers clues about its violent past. For example, the presence of certain stellar populations, such as old, metal-rich stars, can indicate the intensity and duration of the galaxy's quasar phase. These stars often bear the chemical signatures of elements forged in the quasar's outflows, acting as fossil records of the galaxy's energetic history. By studying these stellar populations, astronomers can reconstruct the timeline of the galaxy's evolution, piecing together how its quasar phase influenced its current state. The eventual transformation of quasars into passive galaxies also holds profound implications for the cosmic web, the vast, interconnected structure of matter that spans the universe. Quasars, through their powerful winds and radiation, shape the intergalactic medium, creating vast bubbles of ionized gas. These bubbles persist long after the quasar itself has dimmed, affecting the flow of matter along the filaments of the cosmic web. In some cases, the remnants of quasar activity can suppress the formation of new galaxies by heating the surrounding gas, preventing it from cooling and condensing into stars. In others, these remnants can trigger star formation by compressing gas in neighboring regions. This dual role, both fostering and inhibiting galactic growth, highlights the complex interplay between quasars and their environments. It also underscores the importance of scale in understanding cosmic processes. While quasars operate on the level of individual galaxies, their influence extends across intergalactic distances, connecting the fates of seemingly isolated systems. This interconnectedness is a recurring theme in astrophysics, reminding us that no object in the universe exists in isolation. The study of quasars and their transition into passive galaxies has also sparked new questions about the ultimate fate of these systems. As their energy sources dwindle, and their black holes consume the last remnants of accretion material, what happens next? Do these black holes remain dormant forever, or could they reignite under the right conditions? Recent discoveries suggest that some dead galaxies can experience a second phase of activity, triggered by the accretion of material from a merger or the inflow of gas from the cosmic web. These rejuvenated systems blur the lines between active and passive galaxies, revealing a continuum of states rather than a binary classification. The mystery deepens when considering the role of dark matter in quasar evolution. Dark matter, an invisible substance that makes up most of the universe's mass, is thought to play a crucial role in galaxy formation and stability. During the quasar phase, the interaction between the central black hole and the surrounding dark matter halo may influence the galaxy's ability to sustain or suppress star formation. Some theories propose that dark matter halos act as reservoirs of cold gas, feeding the black hole and sustaining quasar activity. Others suggest that dark matter might mitigate the impact of quasar-driven outflows, allowing galaxies to retain enough material for future star formation. Understanding this relationship is an active area of research, with the potential to revolutionize our understanding of both quasars and dark matter. The life cycle of quasars also invites philosophical questions about the nature of change and permanence in the universe. These objects, which once outshone entire galaxies, eventually fade into obscurity, their brilliance reduced to a quiet gravitational presence. Yet, their influence endures, written into the stars, gas, and structure of their host galaxies. This duality, between the ephemeral and the enduring, mirrors the broader rhythms of the cosmos, where cycles of creation and destruction drive the evolution of all things. Ultimately, the story of quasars is a story of transformation. It is a tale of how raw, chaotic energy gives way to order and stability, of how the most luminous objects in the universe transition into quiet, mature systems. But it is also a story of continuity, of how the echoes of a quasar's activity resonate across cosmic time, shaping the universe in ways we are only beginning to understand. Quasars remind us that even in the face of immense change, the past is never truly lost. It is preserved, woven into the fabric of the cosmos itself. The evolution of quasars into passive galaxies not only reshapes individual systems, but also leaves an indelible mark on the broader universe. As these once brilliant cosmic engines dim, they carry forward the narrative of cosmic evolution, tying the small-scale intricacies of black hole physics to the grand, sweeping architecture of the cosmos. To appreciate this transition fully, we must delve even deeper into the mechanisms and consequences of their transformation, exploring the profound connections between quasars and the dynamic, interconnected universe they inhabit. The mechanisms driving the cessation of quasar activity are as complex as their ignition. Over time, the accretion disk that feeds the supermassive black hole depletes its available material, gradually reducing the black hole's luminosity. However, this depletion process is far from simple. For instance, some quasars may experience periodic starvation events due to disruptions in their host galaxy's gas supply. These events can result from external factors, such as gravitational interactions with neighboring galaxies, or internal processes, like the feedback mechanisms triggered by the quasar itself. One of the most significant feedback processes involves quasar winds, powerful outflows of charged particles accelerated to relativistic speeds. These winds can expel large amounts of gas from the galaxy's central regions, effectively cutting off the fuel supply to the black hole. The expelled gas often forms vast, elongated structures visible in radio or X-ray wavelengths, serving as evidence of the quasar's waning influence. This feedback mechanism not only starves the quasar but also shapes the galaxy's future by limiting the material available for star formation. Interestingly, the extent of this feedback varies widely among quasars. In some cases, the outflows are powerful enough to eject nearly all the gas from the galaxy, leading to a rapid transition into a passive state. In others, the feedback is more localized, allowing pockets of gas to remain and sustain residual star formation. This variability hints at a delicate interplay between the quasar's energy output, the structure of the host galaxy, and the surrounding environment. Understanding this interplay is a major challenge for astrophysicists, requiring sophisticated simulations and observations across multiple wavelengths. As the quasar fades, its host galaxy undergoes a series of profound changes. Without the intense radiation and winds from the central black hole, the galaxy's interstellar medium begins to cool and settle. This cooling process often leads to the formation of dense molecular clouds, the birthplaces of new stars. Paradoxically, while quasars are often associated with the suppression of star formation, their decline can sometimes trigger a resurgence of stellar activity. This post-quasar starburst phase, though short-lived on cosmic timescales, adds another layer of complexity to the life cycle of galaxies. The eventual outcome of these processes is a galaxy that no longer exhibits the violent activity characteristic of its quasar phase. These passive galaxies, often dominated by older, redder stars, emit light primarily in the optical and infrared wavelengths. Their spectra lack the strong emission lines associated with active galactic nuclei, signaling the absence of significant accretion activity. Yet, even in this passive state, the supermassive black hole remains a defining feature of the galaxy, its gravitational influence shaping the motions of stars and gas in its vicinity. The role of these dormant black holes extends beyond their host galaxies. In galaxy clusters, where hundreds or even thousands of galaxies coexist in close proximity, the combined gravitational pull of these black holes contributes to the overall dynamics of the cluster. This cumulative effect, though subtle, helps stabilize the cluster's structure, preventing smaller galaxies from being ejected by gravitational interactions. In this sense, the legacy of quasars persists on scales far larger than individual galaxies, underscoring their importance in the cosmic hierarchy. The connection between quasars and galaxy clusters also raises intriguing questions about the role of environment in quasar evolution. For example, observations suggest that quasars are more likely to occur in galaxies undergoing mergers or interactions. These events funnel gas toward the galactic center, providing the fuel necessary for quasar activity. In dense cluster environments, where such interactions are more frequent, the likelihood of quasar formation and subsequent reactivation may be higher. This environmental dependence highlights the importance of external factors in shaping the life cycle of quasars and their host galaxies. At the same time, quasars influence their environments in ways that extend far beyond their immediate vicinity. Through their outflows and radiation, they can heat the surrounding intergalactic medium, creating vast regions of ionized gas. These ionized regions, often visible as bubbles in maps of the cosmic microwave background, serve as markers of quasar activity in the early universe. By studying these bubbles, astronomers can gain insights into the timing and distribution of quasars, as well as their impact on the large-scale structure of the universe. The transition from quasar to passive galaxy is also intimately linked to the broader question of cosmic time. In the early universe, quasars were far more common, reflecting the abundance of cold gas available for accretion. As the universe aged and this gas supply dwindled, the frequency of quasar activity declined, giving way to a more quiescent cosmic era dominated by passive galaxies. This shift marks a key phase in the evolution of the universe, illustrating how changes in the availability of raw materials drive the life cycle of cosmic structures. Yet, even in the current epoch, the echoes of past quasar activity remain visible. Some galaxies exhibit faint emission lines in their spectra, suggesting residual accretion activity around their central black holes. These fossil quasars offer valuable clues about the long-term evolution of galaxies, providing a bridge between the active and passive phases of their life cycles. By studying these systems, astronomers can better understand the processes that govern the transition from quasar to passive galaxy, shedding light on the intricate interplay between black holes, stars, and gas. Moreover, the study of quasars and their transformation has profound implications for our understanding of the universe's ultimate fate. As the cosmos continues to expand, the availability of gas for star formation and black hole accretion will decline, leading to a gradual dimming of its brightest objects. Quasars, once the beacons of cosmic activity, will become increasingly rare, their remnants confined to the cores of dark, quiet galaxies. This sobering vision of the future underscores the transience of even the most luminous phenomena, reminding us of the impermanence that defines the universe. The story of quasars is far from complete. With advances in technology, such as next-generation telescopes and high-resolution simulations, astronomers are poised to uncover new insights into their life cycles and their impact on the universe. These discoveries will not only deepen our understanding of quasars but also illuminate the broader processes that drive the evolution of the cosmos. As we continue to explore these enigmatic objects, we are reminded of the interconnectedness of all things, from the smallest particle to the largest galaxy, and the enduring mysteries that lie at the heart of the universe. The legacy of quasars stretches far beyond their initial burst of brilliance, intertwining with the universe's history and its future trajectory. To fully grasp their importance, we must consider their role in shaping cosmic structures, their contributions to galaxy evolution, and the ripple effects they create in the fabric of space-time itself. These enigmatic objects are not just relics of a bygone cosmic era, they are active participants in the ongoing story of the universe. One of the most intriguing aspects of quasars is their connection to dark matter and dark energy, two of the most mysterious components of the universe. Quasars, by virtue of their luminosity, provide a powerful tool for probing these elusive forces. Their immense brightness allows astronomers to trace the distribution of matter, both visible and invisible, across vast distances. By studying the light emitted by quasars and how it interacts with intervening matter, scientists can map the large-scale structure of the universe, revealing the intricate web of filaments and voids that make up the cosmic landscape. This mapping process has led to groundbreaking discoveries about the distribution of dark matter. The gravitational lensing of quasar light, where the light bends around massive objects like galaxy clusters, provides direct evidence of dark matter's presence. These lenses act as natural telescopes, magnifying the quasar's light and allowing astronomers to study their properties in unprecedented detail. Through these studies, we gain insights into the mass and distribution of dark matter, offering clues about its nature and its role in the universe's evolution. Quasars also serve as cosmic milestones, marking key events in the universe's history. Their light carries information about the conditions of the early universe, offering a glimpse into the epoch of reionization, a time when the first galaxies and quasars began to form, ionizing the neutral hydrogen that filled the cosmos. By analyzing the spectra of quasars, astronomers can reconstruct the timeline of reionization, shedding light on how and when the universe transitioned from darkness to light. The interplay between quasars and their environments further underscores their importance. As quasars emit immense amounts of energy, they influence the surrounding intergalactic medium, heating and ionizing vast regions of space. This process, known as feedback, plays a critical role in regulating star formation and shaping the properties of galaxies. Quasars can both trigger and suppress star formation, depending on the circumstances, highlighting their dual role as creators and destroyers in the cosmic ecosystem. The impact of quasar feedback extends to the largest structures in the universe, galaxy clusters. These massive assemblies of galaxies are held together by the gravitational pull of dark matter, with their cores often housing supermassive black holes. Quasars within these clusters can inject energy into the intracluster medium, the hot, diffuse gas that permeates the space between galaxies. This energy injection prevents the gas from cooling and condensing into new stars, regulating the growth of galaxies within the cluster. This delicate balance between heating and cooling underscores the complex interplay between quasars and their environments, shaping the evolution of galaxies on both small and large scales. Despite their transformative impact, quasars are not eternal. As their fuel supply dwindles, they transition into a quieter phase, leaving behind a dormant supermassive black hole at the galaxy's core. These inactive black holes, though no longer accreting material, remain a defining feature of their host galaxies. Their gravitational influence continues to shape the motions of stars and gas, anchoring the galaxy's structure and contributing to its stability. Interestingly, not all dormant black holes remain inactive forever. In some cases, external events such as galaxy mergers can reignite quasar activity. These events funnel fresh gas toward the galactic center, sparking a new phase of accretion and luminosity. This cyclical nature of quasar activity highlights the dynamic and ever-changing nature of galaxies, where periods of intense activity alternate with phases of relative quiescence. The study of quasars also provides a window into the physics of extreme environments. The regions near a supermassive black hole are among the most extreme places in the universe, with temperatures, pressures, and magnetic fields that defy comprehension. By studying quasars, scientists can test the limits of our understanding of physics, exploring phenomena like relativistic jets, magnetic reconnection, and the behavior of matter under intense gravitational forces. These studies not only deepen our understanding of quasars but also have implications for other fields of physics, from plasma science to general relativity. As we look to the future, the study of quasars is poised to enter a new era. Next-generation observatories like the James Webb Space Telescope, JWST, and the Vera C. Rubin Observatory are set to revolutionize our understanding of these objects. These telescopes will allow astronomers to study quasars in unprecedented detail, probing their properties and their environments with greater precision than ever before. From identifying the earliest quasars in the universe to mapping their influence on cosmic structures, these observatories promise to unveil new insights into the life cycle of quasars and their role in the cosmos. Moreover, the advent of machine learning and artificial intelligence is opening new avenues for quasar research. These technologies enable astronomers to analyze vast datasets, identifying patterns and correlations that would be impossible to discern manually. By applying these tools to quasar observations, scientists can uncover hidden relationships between quasars and their host galaxies, shedding light on the factors that drive their evolution and their eventual transformation into passive galaxies. Ultimately, the study of quasars is a testament to the interconnectedness of the universe. These luminous beacons, born from the chaotic dance of matter and energy, illuminate not only the regions around them but also the broader processes that shape the cosmos. Their life cycle, from brilliant quasars to quiet, passive galaxies, mirrors the story of the universe itself, a tale of creation, transformation, and eventual decline. As we continue to explore these enigmatic objects, we are reminded of the profound beauty and complexity of the cosmos, and our place within it. The transformation of quasars into passive galaxies encapsulates the life cycle of the most energetic objects in the universe, but their story remains an ongoing puzzle. At the heart of this transformation lies the relationship between quasars and the host galaxies that nurture and sustain them. As their activity fades, the once turbulent regions surrounding the supermassive black hole settle into a calmer state. Yet, the processes that drive this shift, from high-energy emission to subdued passivity, continue to challenge our understanding of cosmic evolution. When quasars exhaust their primary fuel supply, the accretion disk begins to dissipate. Without a steady inflow of matter to sustain the intense radiation, the supermassive black hole becomes dormant. The once blazing quasar transitions into a galaxy with a faint or non-existent active galactic nucleus, AGN. This marks the beginning of a quieter phase in the galaxy's life, characterized by reduced energy output and fewer dramatic interactions with its surroundings. The exact timeline of this transformation depends on several factors, including the initial mass of the black hole, the availability of gas and dust, and the galaxy's environment. For instance, galaxies located in dense clusters may experience a faster decline in quasar activity due to interactions with neighboring galaxies or the stripping of gas by the cluster's intragalactic medium. Conversely, isolated galaxies may sustain their quasar phase longer, provided they have an ample supply of fuel. As the quasar phase wanes, the galaxy enters a phase often described as red and dead. This term refers to the absence of significant star formation and the dominance of older, redder stars in the galaxy's population. Without the influx of fresh gas, the formation of new stars slows or ceases altogether. Over time, the galaxy's light becomes dominated by the faint glow of aging stars, giving it a more subdued appearance compared to its active, quasar-driven past. The role of feedback mechanisms in this transition cannot be overstated. During its active phase, a quasar releases immense amounts of energy into its surroundings, driving powerful winds and jets that can eject gas from the galaxy's core. This feedback process not only curtails star formation but also helps to deplete the fuel supply necessary for sustained quasar activity. As a result, the quasar effectively shuts itself off, paving the way for its host galaxy to evolve into a more passive state. However, this transition is not always smooth. Observations have revealed instances of galaxies that show signs of recent quasar activity, even though they appear to be largely passive. These galaxies, sometimes referred to as post-starburst or quench galaxies, provide a glimpse into the intermediate stages of quasar evolution. Their properties suggest that the shift from an active quasar to a passive galaxy may involve periods of intermittent activity, where bursts of star formation or black hole accretion are interspersed with quiescent phases. The remnants of a quasar's active phase can also leave an indelible mark on its host galaxy. For example, the powerful winds generated during the quasar phase can alter the galaxy's structure, creating large-scale outflows that shape its morphology. These winds can clear out the central regions of the galaxy, leaving behind a more diffuse distribution of stars and gas. In some cases, these outflows may even create observable features, such as elongated tidal tails or disrupted stellar populations, that serve as lasting evidence of the galaxy's tumultuous past. Interestingly, not all galaxies with supermassive black holes experience a quasar phase. The conditions necessary for quasar activity, namely, a high rate of gas inflow into the central black hole, are not universally met. Many galaxies harbor dormant black holes that have never undergone a quasar phase, suggesting that the interplay between a galaxy's environment, its internal dynamics, and its cosmic history determines whether it will host an active quasar. The study of quasar evolution also provides crucial insights into the broader context of galaxy evolution. Quasars are often found in massive galaxies, particularly those located in dense environments like galaxy clusters. Their presence is closely linked to the growth of supermassive black holes, which, in turn, influences the overall evolution of their host galaxies. By understanding the life cycle of quasars, scientists can piece together the complex web of interactions that govern the growth and transformation of galaxies across cosmic time. As we probe deeper into the universe, new technologies are enabling more detailed studies of quasars and their host galaxies. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Extremely Large Telescope, ELT, are providing unprecedented views of these objects, revealing their properties at different stages of their evolution. These observations are helping to refine our understanding of the factors that drive the transition from an active quasar to a passive galaxy, as well as the long-term consequences of this transformation. The future of quasar research also hinges on the ability to simulate their evolution using advanced computational models. These simulations allow scientists to explore the interplay between quasars, their host galaxies, and the larger cosmic environment, offering a virtual laboratory for testing theories and making predictions. By comparing these models to observational data, researchers can identify the key processes that govern quasar evolution and their impact on the universe as a whole. The story of quasars is far from complete. As our understanding deepens, new questions continue to emerge, challenging us to rethink our assumptions and explore new possibilities. What triggers the onset of quasar activity in some galaxies but not others? How do quasars influence the formation and growth of large-scale cosmic structures? And what role do they play in the ultimate fate of the universe? These questions highlight the enduring mystery of quasars and their significance in the grand tapestry of the cosmos. Quasars are not just fascinating objects in their own right. They are windows into the universe's past, present, and future. Their life cycle, from blazing beacons of energy to quiet, passive galaxies, mirrors the broader processes that shape the cosmos, offering a glimpse into the forces that govern the evolution of everything from individual stars to entire galaxies. As we continue to unravel their mysteries, quasars remind us of the beauty and complexity of the universe, and the endless possibilities for discovery that lie ahead. The role of quasars in shaping their host galaxies becomes even more intriguing when we consider the scale of their influence. Despite being confined to the central regions of galaxies, quasars exert control over vast areas through their outflows, jets, and radiation. These mechanisms don't just impact the immediate vicinity of the supermassive black hole. They extend to influence star formation across the galaxy and even beyond, into the intergalactic medium. Quasar winds, driven by the intense radiation pressure near the accretion disk, are among the most significant factors in this influence. These winds, traveling at speeds of thousands of kilometers per second, carry gas and dust away from the central regions of the galaxy. This ejection of material can suppress star formation by removing the raw ingredients needed to form new stars. Yet, paradoxically, these same winds can trigger star formation under certain conditions, compressing clouds of gas in the galaxy's outskirts and sparking the birth of new stars. This dual role of quasar feedback, both destructive and creative, is a prime example of the complexity inherent in galaxy evolution. The balance between these effects depends on factors like the density and distribution of gas within the galaxy, the strength of the quasar's outflows, and the galaxy's environment. In some cases, feedback may predominantly quench star formation, leading to the eventual transition into a passive galaxy. In others, it may create temporary bursts of star formation before the galaxy settles into quiescence. Jets, another hallmark of quasar activity, add yet another layer of complexity. These highly collimated streams of charged particles are launched from the regions near the black hole at nearly the speed of light. They pierce through the galaxy, sometimes extending hundreds of thousands of light-years into intergalactic space. Like winds, jets can suppress star formation by heating or ejecting gas, but they can also compress gas in certain regions, leading to localized bursts of star formation. The effects of jets are particularly pronounced in radial-loud quasars, which are among the most powerful energy sources in the universe. Radiation from the quasar itself also plays a crucial role in shaping the galaxy's evolution. The intense light emitted by the accretion disk can ionize gas, preventing it from cooling and collapsing to form stars. This effect, known as radiative feedback, is particularly significant in the early stages of a galaxy's life when large reservoirs of gas are available. Over time, radiative feedback can deplete these reservoirs, contributing to the eventual decline of star formation and the galaxy's transition to a passive state. The cumulative impact of these feedback mechanisms is evident in the large-scale properties of galaxies and their environments. Observations of galaxy clusters, for example, revealed the presence of enormous cavities in the hot gas that fills these clusters, carved out by quasar-driven winds and jets. These features, often referred to as bubbles or lobes, provide direct evidence of the energy deposited by quasars over millions of years. Such observations highlight the far-reaching influence of quasars, extending well beyond their host galaxies. Interestingly, not all galaxies respond to quasar activity in the same way. Some galaxies, particularly those with dense central regions, may retain enough gas to sustain star formation even in the presence of strong feedback. Others, especially those in dense environments like galaxy clusters, may lose their gas more rapidly, accelerating their transition into passive galaxies. This diversity underscores the importance of local conditions in determining the outcome of quasar activity. As galaxies evolve, the remnants of their quasar phase may leave behind clues that can be detected billions of years later. For example, the presence of supermassive black holes in the centers of massive galaxies is a direct legacy of their quasar past. These black holes, though dormant, continue to influence their host galaxies through their gravitational pull and occasional low-level activity. Observations of dormant black holes in nearby galaxies provide valuable insights into the long-term consequences of quasar activity and the processes that govern their evolution. The connection between quasars and their host galaxies also extends to the larger cosmic web. Quasars, particularly during their peak activity in the early universe, played a significant role in shaping the intergalactic medium, the vast expanse of gas and dark matter that connects galaxies. By ionizing and heating this medium, quasars contributed to the reionization of the universe, a pivotal event in cosmic history. This influence, though largely indirect, underscores the interconnected nature of cosmic structures and the central role of quasars in shaping them. Despite the progress made in understanding quasars and their evolution, many questions remain unanswered. For instance, the exact mechanisms that trigger the onset of quasar activity are still not fully understood. While interactions and mergers between galaxies are known to play a role, the details of how these processes funnel gas into the central black hole are still a topic of active research. Similarly, the factors that determine the duration of the quasar phase and the rate at which it declines are not yet fully understood. Advances in observational technology are helping to address these questions. Instruments like the James Webb Space Telescope, JWST, are providing unprecedented views of quasars and their host galaxies, allowing scientists to study their properties in greater detail than ever before. These observations are complemented by theoretical models and simulations, which provide a framework for interpreting the data and making predictions about the life cycle of quasars. As we continue to explore the universe, quasars remain among the most intriguing and enigmatic objects in existence. Their evolution, from brilliant cosmic lighthouses to quiet, mature galaxies, mirrors the broader processes that govern the growth and transformation of galaxies across cosmic time. By unraveling the mysteries of quasars, we gain not only a deeper understanding of the universe but also a glimpse into our own origins, as the stars and planets that make up our world were born from the same cosmic processes that fuel these extraordinary objects. The transformation of quasars into passive galaxies marks one of the most dramatic transitions in the cosmic life cycle. But to fully appreciate its complexity, we must delve deeper into the underlying processes and the rich tapestry of events that lead to this evolution. While we've touched on the roles of quasar winds, jets, and radiative feedback, the interplay between these elements and the broader galactic environment deserves even closer examination. A key factor in the life cycle of quasars is the availability of cold gas, the essential fuel for both accretion onto the supermassive black hole and star formation. During a quasar's peak activity, the central black hole consumes vast quantities of this gas, pulling it into the accretion disk and generating the intense luminosity that defines quasars. However, this phase is inherently self-limiting. The very processes that sustain a quasar's brilliance, such as powerful outflows and intense radiation, are the same ones that deplete or expel the gas, effectively shutting down the system over time. Interestingly, the timescale of this depletion varies significantly depending on the galaxy's mass and environment. In massive galaxies, the gravitational potential is strong enough to retain some of the gas ejected by quasar feedback, potentially allowing for a longer phase of star formation. In contrast, smaller galaxies may lose their gas more rapidly, accelerating their evolution into passive systems. This difference in behavior is one reason why the largest galaxies, such as ellipticals, often host supermassive black holes that were once powerful quasars but are now dormant. The transition from an active quasar to a passive galaxy is not a sudden event. It unfolds over millions of years, with multiple stages that can often overlap. After the most intense quasar activity subsides, galaxies may go through a post-quasar phase where residual accretion continues at lower levels. These systems, often referred to as low-luminosity active galactic nuclei (AGNs), exhibit some of the characteristics of quasars but lack their extreme brightness. Observing these objects provides a unique opportunity to study the cool-down phase of quasar evolution and the lingering effects of their past activity. One of the lingering effects is the structural transformation of the host galaxy itself. Observations have shown that galaxies hosting quasars often have disturbed morphologies, including tidal tails, shells, and other features indicative of recent interactions or mergers. These interactions are thought to play a critical role in triggering quasar activity by funneling gas toward the central regions of the galaxy. However, once the quasar phase ends, the galaxy begins to settle into a more stable configuration. Over time, the chaotic structures are smoothed out, and the galaxy takes on a more regular appearance, often becoming an elliptical or lenticular galaxy. The cessation of star formation in these galaxies is another hallmark of their transition. While feedback mechanisms play a significant role in shutting down star formation, other factors also contribute. For instance, as the galaxy ages, the gas within it may become too hot or diffuse to form stars efficiently. Additionally, the depletion of cold gas reservoirs due to accretion onto the black hole and star formation itself leaves little material for future stellar generations. This process, known as gas exhaustion, ensures that the galaxy's stellar population becomes increasingly dominated by older, redder stars, a characteristic feature of passive galaxies. However, even in their quiescent state, these galaxies are not entirely lifeless. Observations have revealed faint but persistent activity in many so-called dead galaxies. This activity, often in the form of weak jets or low-level accretion onto the central black hole, suggests that the quasar phase never truly ends but rather fades into the background. This residual activity may play a subtle yet important role in maintaining the passive state of the galaxy by preventing the cooling and condensation of gas that could otherwise reignite star formation. The interplay between quasars and their surrounding environments also extends to the large-scale structures of the universe. Quasars are often found in regions of high galaxy density, such as clusters or groups, where interactions and mergers are more common. These environments not only facilitate the inflow of gas needed to sustain quasar activity, but also amplify the effects of quasar feedback. For example, the powerful outflows and jets from quasars can heat the intracluster medium, suppressing the formation of new galaxies and altering the overall evolution of the cluster. This interconnectedness is further highlighted by the role of quasars in cosmic reionization, a pivotal epoch in the early universe when the first stars and galaxies transformed the surrounding neutral hydrogen into an ionized state. Quasars, with their intense ultraviolet radiation, were among the most powerful sources of ionizing photons during this period. By studying distant quasars, astronomers can gain insights into the conditions of the early universe and the processes that shaped its evolution. The study of quasars also raises intriguing questions about the fate of their host galaxies on even longer timescales. As the universe continues to expand and evolve, the interactions between galaxies become less frequent, and the overall rate of star formation declines. In this context, the passive galaxies that were once home to quasars may represent a glimpse into the distant future of all galaxies, a time when star formation has largely ceased, and the universe is dominated by ancient, slowly fading stellar systems. Moreover, the remnants of quasar activity, particularly supermassive black holes, remain as silent witnesses to their turbulent past. These black holes, though dormant, continue to influence their host galaxies through their gravitational effects and occasional bursts of activity. Observations of nearby galaxies have revealed fascinating correlations between the mass of these black holes and the properties of their host galaxies, such as the mass of the central bulge or the velocity dispersion of stars. These correlations, known as scaling relations, suggest a deep and enduring connection between the growth of black holes and the evolution of galaxies. While much has been learned about quasars and their role in galaxy evolution, the field is far from fully understood. Many mysteries remain, from the precise mechanisms that trigger quasar activity to the details of how feedback processes operate on different scales. Future observations with advanced telescopes, such as the James Webb Space Telescope and next-generation radio arrays, promise to shed light on these questions, revealing new facets of the quasar life cycle and its impact on the universe. As we gaze deeper into the cosmos, quasars remind us of the immense power and complexity of the universe. Their evolution, from brilliant beacons to quiet, mature galaxies, encapsulates the dynamic processes that have shaped the cosmos over billions of years. By unraveling the secrets of quasars, we not only deepen our understanding of the universe but also uncover the threads that connect us to its vast and ever-changing tapestry. The journey of quasars into passive galaxies remains a powerful narrative within cosmic history, highlighting the transformation of some of the most energetic phenomena into tranquil systems that silently populate the universe today. But this narrative invites even more questions. How universal is this life cycle? Are there exceptions or alternate pathways for galaxies with active nuclei? What does this mean for our understanding of galactic evolution and the ultimate fate of the universe itself? To probe deeper, we must revisit the mechanisms that allow quasars to switch off, focusing on the complex interplay between feedback processes and environmental factors. Feedback, whether radiative or kinetic, is central to this transition. Radiative feedback operates through the immense energy output of a quasar, which ionizes, heats, and ultimately drives gas out of the galaxy's core. This process creates regions of high-temperature plasma, observable in X-ray wavelengths, that can persist for billions of years, inhibiting the cooling of gas that would otherwise trigger star formation. Kinetic feedback, on the other hand, manifests as physical outflows like winds and relativistic jets. These jets, composed of charged particles accelerated to near-light speeds, extend far beyond the host galaxy, interacting with the intergalactic medium. In doing so, they create large-scale cavities or bubbles in surrounding gas clouds, redistributing matter and energy over vast regions. While jets are among the most dramatic signatures of active galactic nuclei, AGN, their effects are not limited to a single galaxy. They can influence the dynamics of galaxy clusters, heating their intra-cluster medium and contributing to the large-scale structure of the universe. The variability in feedback processes introduces another layer of complexity. Not all quasars follow a straightforward evolutionary path. Some exhibit episodic activity, where bursts of accretion and energy output alternate with periods of quiescence. This phenomenon, often referred to as AGN flickering, challenges the notion of a single, continuous phase of activity. Instead, it suggests that the quasar life cycle may be more cyclical, influenced by the inflow of gas from external sources, such as satellite galaxies or cosmic filaments, that temporarily reignite the central engine. This episodic behavior has profound implications for the coevolution of galaxies and their central black holes. If a quasar's activity can be reignited multiple times, its cumulative impact on the host galaxy and surrounding environment could be much greater than previously thought. For instance, successive episodes of feedback might lead to repeated cycles of starburst activity followed by quiescence, shaping the galaxy's stellar population in ways that are not yet fully understood. Moreover, the physical properties of the host galaxy itself play a crucial role in determining the nature and duration of quasar activity. Galaxies with dense, gas-rich disks are more likely to sustain prolonged periods of accretion, as the availability of fuel allows the black hole to maintain its energetic output. Conversely, galaxies with sparse or diffuse gas reservoirs may experience shorter, less intense phases of quasar activity. This variability underscores the importance of initial conditions, such as a galaxy's mass, morphology, and location within the cosmic web, in shaping its evolutionary trajectory. A particularly intriguing aspect of this relationship is the role of mergers and interactions. Observational evidence strongly suggests that galaxy mergers are a primary trigger for quasar activity. When two galaxies collide, their gravitational forces disrupt the distribution of gas and stars, funneling vast amounts of material toward their central regions. This inflow feeds the supermassive black holes, initiating the quasar phase. However, the aftermath of these mergers often leaves behind a dramatically transformed system, with altered morphologies and depleted gas supplies that pave the way for the galaxy's eventual transition to passivity. Interestingly, not all mergers lead to quasar activity. In some cases, the interaction may result in a more gradual redistribution of gas, allowing for sustained star formation without triggering the intense accretion associated with quasars. These subtler interactions highlight the diversity of galactic outcomes and the many factors that influence whether a galaxy becomes a quasar host or evolves along a different path. Another factor to consider is the role of dark matter, the enigmatic substance that constitutes a significant portion of the universe's mass. dark matter halos provide the gravitational scaffolding for galaxies, influencing their structure, dynamics, and ability to retain gas. The interplay between dark matter and feedback processes from quasars is an active area of research, with implications for everything from the formation of galaxy clusters to the distribution of cosmic voids. Despite these complexities, the eventual outcome for most quasars is clear. They transition into passive galaxies, characterized by low levels of star formation and minimal central activity. These galaxies, often ellipticals or lenticulars, dominate the local universe, representing the final stages of galactic evolution. However, even in their quiescent state, they retain the imprints of their active past. For example, the presence of a supermassive black hole at their core, even if dormant, serves as a reminder of the galaxy's turbulent history. This transformation also raises questions about the ultimate fate of these passive galaxies. As the universe continues to expand, the frequency of galaxy interactions and mergers decreases, leading to a more isolated and static environment. In this context, passive galaxies may become increasingly disconnected from their surroundings, evolving into isolated systems where stellar populations age and fade without renewal. On the largest scales, the evolution of quasars into passive galaxies reflects broader trends in cosmic history. The peak era of quasar activity, often referred to as cosmic noon, occurred around 10 billion years ago, when the universe was rich in gas and galaxy interactions were frequent. Since then, the rate of star formation and quasar activity has declined, signaling a shift toward a quieter, more stable universe. This transition mirrors the life cycle of individual quasars, offering a microcosm of the universe's broader evolution. Yet, for all we know, many mysteries remain. Why do some galaxies sustain quasars for longer periods than others? What governs the variability in feedback processes? And how do these factors influence the large-scale structure of the universe? These questions continue to drive research, promising new discoveries that will deepen our understanding of quasars and their role in shaping the cosmos. As we reflect on the evolution of quasars into passive galaxies, we are reminded of the dynamic, interconnected nature of the universe. From the violent energy of quasars to the serene stability of mature galaxies, this transformation captures the essence of cosmic change, offering a glimpse into the forces that have shaped the universe and our place within it. The transformation of quasars into passive galaxies not only highlights the life cycle of these energetic cosmic entities but also illuminates the broader evolutionary patterns that define the universe. This process exemplifies how galaxies evolve from chaotic, high-energy systems to stable, mature structures. But even as passive galaxies dominate the universe today, the remnants of their quasar phase continue to exert influence, subtly shaping the future of the cosmos. One of the most fascinating aspects of this evolutionary narrative is the long-term role of supermassive black holes. Even in their dormant state, these colossal objects retain the potential to awaken under the right conditions. While the gas reservoirs in most passive galaxies are depleted, external factors such as minor mergers or accretion of intergalactic gas can occasionally reignite accretion processes. These rare events might trigger brief periods of renewed activity, producing what astronomers call low-luminosity AGN. These episodes, while far less dramatic than the original quasar phase, remind us that the life cycle of galaxies and their central black holes is never entirely static. The role of external gas accretion becomes especially intriguing when considering the cosmic environment. In dense galaxy clusters, where galaxies are tightly packed and gas-rich environments prevail, the likelihood of interaction-induced activity increases. Conversely, in more isolated regions, passive galaxies may continue to age quietly, undisturbed by their surroundings. This environmental dependency underscores the importance of a galaxy's location within the cosmic web, emphasizing how large-scale structure influences individual systems. As passive galaxies age, their stellar populations evolve, and their light output gradually dims. This process, known as stellar population aging, provides valuable clues about a galaxy's history. By studying the distribution of stars, their metallicity, and their kinematics, astronomers can reconstruct the timeline of a galaxy's quasar phase, its star formation history, and its ultimate transition to passivity. This forensic approach reveals the enduring legacy of quasars, encoded in the very fabric of their host galaxies. Another critical piece of the puzzle lies in the relationship between supermassive black holes and dark matter. While black holes dominate the central regions of galaxies, dark matter extends far beyond, forming vast halos that envelop entire systems. These halos play a pivotal role in stabilizing galaxies, counteracting the forces that would otherwise lead to their disintegration. Yet, the interaction between dark matter and baryonic matter, such as stars, gas, and black holes, remains poorly understood. How does the presence of a dark matter halo influence the accretion processes that power quasars? Does it provide a protective environment that allows for prolonged activity, or does it act as a gravitational well, trapping outflows and inhibiting feedback? These questions remain at the forefront of astrophysical research. Looking beyond individual galaxies, the evolution of quasars into passive galaxies offers a window into the broader timeline of the universe. During the quasar epoch, the cosmos was a bustling, dynamic place, teeming with energy and rapid transformation. Galaxies collided, black holes fed voraciously, and star formation rates soared. Today, the universe has entered a more subdued phase, where passive galaxies far outnumber active ones, and the rate of cosmic activity has significantly declined. This transition reflects the cooling of the universe as a whole, marking the gradual shift from a young, vibrant cosmos to a more mature and stable one. However, the story doesn't end there. The eventual fate of passive galaxies, and the universe itself, remains an open question. As the universe continues to expand at an accelerating rate, driven by the mysterious force of dark energy, galaxies are moving farther apart. Over billions of years, this expansion will lead to a scenario where galaxies become increasingly isolated, their interactions dwindling to near zero. In such a future, passive galaxies will drift through the cosmic void, their light fading as their stars exhaust their nuclear fuel. This vision of the end state of the universe, sometimes referred to as the heat death, paints a picture of a cosmos dominated by dark, lifeless galaxies. Yet, even in this seemingly bleak scenario, the remnants of quasars and their host galaxies offer a profound reminder of the universe's dynamic history. The supermassive black holes at the centers of these galaxies, though dormant, remain as silent witnesses to the cosmic drama that once unfolded. The study of quasars and their evolution also serves as a powerful tool for understanding fundamental physics. Quasars act as cosmic lighthouses, their intense energy output illuminating the intergalactic medium and revealing the distribution of matter on vast scales. By analyzing the light from distant quasars, astronomers can probe the composition of the early universe, detect the presence of primordial gas clouds, and even test theories of gravity and cosmology. In this sense, quasars are not just relics of the past but active participants in our quest to understand the universe. Moreover, the transition from quasar to passive galaxy challenges us to think about the interconnectedness of cosmic phenomena. It highlights how processes operating on vastly different scales, from the accretion of gas onto a black hole to the large-scale structure of the universe, are intricately linked. This interconnectedness is a testament to the complexity and beauty of the cosmos, where no single event or object exists in isolation. As we continue to study the evolution of quasars into passive galaxies, new technologies promise to deepen our understanding. Advanced telescopes like the James Webb Space Telescope, JWST, and next-generation observatories will allow us to peer deeper into the universe than ever before, uncovering the faint signatures of early quasars and tracing their evolution across cosmic time. These observations will not only refine our models of galactic evolution but also shed light on the broader mechanisms that govern the universe. The journey of quasars, from their energetic beginnings to their quiet maturity, is a story of transformation, resilience, and interconnectedness. It is a reminder that even the most powerful phenomena are subject to the forces of change, evolving in ways that shape the universe as we know it. As we unravel the mysteries of this process, we gain not only a deeper understanding of cosmic history but also a profound appreciation for the dynamic nature of existence itself. The transformation of quasars into passive galaxies is emblematic of the intricate, interwoven processes that define the universe. While it may seem like a straightforward narrative, a fiery, energetic beginning transitioning to a quiet, stable end, the details reveal layers of complexity that continue to challenge and inspire astronomers. To fully appreciate this journey, it's worth exploring the long-lasting implications of these transformations on a variety of scales, from individual galaxies to the entire cosmic web. At the heart of every quasar lies a supermassive black hole, and the eventual quieting of these objects represents a profound shift in the life of a galaxy. During their active phase, quasars generate immense energy, often outshining the combined light of all the stars in their host galaxy. This energy is not only a byproduct of matter spiraling into the black hole, but also a driving force for galaxy-wide changes. The intense radiation and powerful outflows from quasars regulate star formation, heat interstellar gas, and even expel material beyond the confines of the galaxy. Yet, as the quasar phase winds down and the black hole enters a more dormant state, these feedback processes cease, leaving a galaxy that must adapt to a quieter existence. The transition to a passive galaxy is typically marked by the depletion of cold gas, the primary ingredient for star formation. Without a fresh supply of this material, star formation slows to a trickle or halts altogether. This depletion is often the result of quasar-driven winds and jets, which can expel gas at astonishing speeds, sometimes exceeding thousands of kilometers per second. Additionally, the gravitational interactions that frequently accompany galaxy mergers, the very events that often trigger quasar activity, can strip galaxies of their gas. Over time, the galaxy's once vibrant spiral arms or chaotic starburst regions settle into a more subdued state, characterized by a spheroidal shape and an aging stellar population. These passive galaxies, often referred to as red and dead, due to their reddish color and lack of new star formation, dominate the universe today. But their apparent dormancy belies a fascinating internal structure. Within these galaxies, stars continue to evolve, and remnants of their quasar past remain embedded in the central regions. The supermassive black holes, though no longer actively accreting matter, still exert a gravitational influence on their surroundings. They anchor the galaxy's core, maintaining its structural integrity, and occasionally disrupting stars that venture too close. The lingering impact of the quasar phase can also be observed in the distribution of elements within the galaxy. During their active period, quasars produce and disperse heavy elements, such as carbon, oxygen, and iron, throughout their host galaxies and into intergalactic space. This enrichment process plays a crucial role in the chemical evolution of the universe, ensuring that subsequent generations of stars and planets form with a diverse array of elements. In this way, the quasar phase contributes not just to the life cycle of a single galaxy but to the broader tapestry of cosmic evolution. Another intriguing aspect of the transition from quasar to passive galaxy is the fate of the galaxy's central black hole. While these black holes are often thought of as dormant, they are rarely entirely inactive. In some cases, residual accretion can produce low-level activity, manifesting as faint emissions detectable in radio or X-ray wavelengths. These phenomena, known as radio mode (AGN), represent the faint echoes of a galaxy's more energetic past. Furthermore, external events, such as the accretion of stray gas or minor galaxy mergers, can reignite activity, albeit on a much smaller scale than during the quasar phase. The presence of a supermassive black hole also influences the galaxy's dark matter halo. These halos, which extend far beyond the visible boundaries of a galaxy, provide the gravitational framework that binds galaxies together. The interplay between the central black hole, the galaxy's stars, and the dark matter halo remains an area of active research. For instance, some theories suggest that the energy output of a quasar during its active phase can affect the distribution of dark matter, potentially redistributing it within the halo. If true, this would imply that the legacy of a quasar phase extends far beyond the visible galaxy, influencing its larger-scale environment. On a cosmic scale, the evolution of quasars into passive galaxies mirrors the broader transition of the universe itself. During the quasar epoch, the universe was a place of intense activity, with galaxies frequently merging, stars forming at rapid rates, and black holes growing at an unprecedented pace. Today, The universe has entered a more quiescent phase, characterized by a lower overall rate of star formation and a prevalence of passive galaxies. This shift reflects the gradual depletion of the gas reservoirs that fueled earlier cosmic activity, as well as the universe's ongoing expansion, which stretches and cools intergalactic matter. The study of quasars and their evolution also provides valuable insights into the conditions of the early universe. By observing distant quasars, astronomers can peer back in time to when the universe was just a few billion years old. These observations reveal the state of intergalactic gas, the formation of the first galaxies, and the emergence of large-scale cosmic structures. Quasars serve as beacons, illuminating the vast expanse of space and providing a window into the processes that shape the cosmos. Technological advancements are opening new doors for studying this transformation. Telescopes like the James Webb Space Telescope are poised to revolutionize our understanding of quasars and their host galaxies. With its ability to observe faint and distant objects in unprecedented detail, the JWST will allow astronomers to study the earliest quasars, trace their growth over time, and investigate their eventual transition into passive galaxies. These observations will not only refine existing theories but also uncover new phenomena that challenge our understanding of galactic evolution. Ultimately, the evolution of quasars into passive galaxies is a testament to the dynamic nature of the universe. It underscores how the most energetic and chaotic phenomena give rise to stability and order, how the actions of a single black hole can shape the fate of an entire galaxy, and how the interplay of forces, both seen and unseen, governs the cosmos. As we continue to unravel this story, we are reminded of the universe's capacity for transformation, its interconnectedness, and its endless capacity to surprise us. The life cycle of quasars transitioning into passive galaxies is not just a study of dramatic celestial events but also a reflection of the universe's broader cycles of creation and transformation. To fully appreciate this, it's crucial to delve deeper into the processes that occur at every stage of this evolution, exploring how each phase leaves its mark on the galaxy, the surrounding environment, and even the larger-scale structure of the cosmos. One of the key elements in understanding this transition is the role of mergers and interactions between galaxies. Galactic collisions are a primary driver of quasar activity. When two galaxies interact, their gravitational forces create tidal disruptions that funnel massive amounts of gas toward their centers. This inflow of material feeds the supermassive black hole at the galaxy's core, igniting the quasar phase. The inflow itself is an intricate process, influenced by factors like the galaxy's relative sizes, the presence of pre-existing structures such as bars or spiral arms, and even the orientation of their spins. Interestingly, the dynamics of these interactions can vary greatly depending on the environment. In dense galaxy clusters, where interactions are more frequent, the likelihood of a galaxy undergoing multiple quasar phases increases. Each of these phases leaves a cumulative imprint, shaping the galaxy's final structure and composition. On the other hand, in more isolated regions, a galaxy may experience a single, brief quasar phase before settling into a quieter state. This environmental dependency highlights the importance of context in galactic evolution, showing that even the same fundamental processes can yield vastly different outcomes depending on the surrounding conditions. Once the quasar phase ends, the galaxy enters a period of significant cooling and stabilization. However, the process of cooling is not as straightforward as it might seem. Residual heat from the quasar's energetic activity, combined with the motions of stars and dark matter within the galaxy, creates a dynamic environment that can take billions of years to settle. Additionally, the expelled gas, often enriched with heavy elements, doesn't simply vanish, it becomes part of the intergalactic medium, contributing to the overall chemical evolution of the universe. The expelled material also interacts with cosmic filaments, the massive, web-like structures of dark matter and gas that form the backbone of the universe's large-scale structure. These filaments act as highways for matter, channeling gas and galaxies toward dense regions like galaxy clusters. The interplay between quasar-driven outflows and these filaments can influence the flow of material on a cosmic scale, potentially altering the growth and evolution of nearby galaxies. Another fascinating aspect of this transition is the residual presence of the supermassive black hole. Even after the quasar phase ends, the black hole remains a dominant force within the galaxy, albeit in a less conspicuous way. These dormant black holes can still exert influence through their gravitational pull, shaping the orbits of stars and other matter in the galaxy's central regions. In some cases, the black hole may continue to accrete small amounts of material, producing faint emissions detectable only with sensitive instruments. These fossil quasars serve as a reminder of the galaxy's energetic past. Moreover, the quieting of a quasar does not mean the black hole is permanently inactive. In rare instances, external events such as the accretion of a wandering gas cloud or a minor galaxy merger can reignite low-level activity. These episodes, often referred to as low-luminosity active galactic nuclei, LOGNs, are a faint echo of the galaxy's former quasar phase. While much less dramatic than the original quasar activity, LOGNs provide valuable insights into the long-term evolution of black holes and their host galaxies. On a broader scale, the transformation of quasars into passive galaxies contributes to the overall evolution of the universe's population of galaxies. During the early universe, quasars were far more common, reflecting a time of rapid growth and intense activity. As the universe aged and its overall energy levels decreased, the prevalence of quasars diminished, giving way to the dominance of passive galaxies. This shift marks a significant turning point in cosmic history, illustrating how the universe evolves from a state of high energy and chaos to one of relative stability and order. The study of this transformation also sheds light on the role of feedback mechanisms in regulating galactic activity. Feedback refers to the processes through which energy and matter expelled by a quasar influence the surrounding environment. These mechanisms are critical for maintaining the delicate balance between growth and stabilization in galaxies. Without feedback, galaxies might consume their gas reserves too quickly, leading to runaway star formation and the eventual collapse of their structures. By expelling gas and heating the interstellar medium, quasars act as a form of cosmic regulation, ensuring that galaxies evolve in a sustainable manner. In recent years, technological advancements have provided new tools for studying these processes in unprecedented detail. Observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the European Southern Observatory's Very Large Telescope, VLT, have allowed astronomers to probe the cold gas reservoirs of galaxies, tracing how these materials are influenced by quasar activity. Similarly, space-based telescopes like Hubble and Chandra have revealed the intricate interplay between quasars, their host galaxies, and the surrounding intergalactic medium. Looking ahead, upcoming missions like the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission promise to further expand our understanding of this fascinating transformation. These instruments will provide deeper insights into the early universe, helping to uncover the origins of quasars and their eventual evolution into passive galaxies. By studying these processes across different epochs, astronomers hope to construct a more complete picture of how galaxies, and the universe as a whole, have evolved over billions of years. In many ways, the evolution of quasars into passive galaxies serves as a microcosm of the universe itself. It encapsulates the dynamic interplay of creation and destruction, the balance of chaos and order, and the interconnectedness of all cosmic phenomena. As we continue to study these transitions, we are reminded of the profound complexity and beauty of the universe, a testament to the countless forces that shape its endless evolution. The story of quasars evolving into passive galaxies also provides a lens through which we can better understand the intricate relationship between black holes and the larger structures they inhabit. Supermassive black holes are not merely gravitational sinks. They are cosmic engines that fundamentally alter the environments around them. The energy they release during their active phases, such as in a quasar, can have both immediate and long-term effects on their host galaxies. To understand these relationships, it's crucial to examine the processes at work during and after the quasar phase. One of the most intriguing aspects of this transformation is the role of radiation pressure and relativistic jets in shaping a galaxy's future. During a quasar's active phase, the supermassive black hole at its center accretes vast amounts of material, often forming a luminous accretion disk. The intense radiation generated by this process exerts outward pressure, known as radiation pressure, which can be powerful enough to expel gas and dust from the galaxy's core. This expulsion is a double-edged sword. While it suppresses further star formation by depleting the gas supply, it also prevents the galaxy from collapsing under its own gravity, allowing it to stabilize over time. In addition to radiation pressure, many quasars produce relativistic jets, narrow beams of highly energetic particles that are ejected perpendicular to the accretion disk. These jets can extend for thousands, or even millions, of light years, interacting with the intergalactic medium and influencing nearby structures. In some cases, the energy from these jets heats the surrounding gas to the point where it cannot cool and condense into new stars. This radio mode feedback mechanism is another way in which quasars regulate their host galaxies, ensuring that star formation occurs at a sustainable rate. Interestingly, the eventual dissipation of these jets and the fading of the accretion disk mark the beginning of a galaxy's transition into a more passive state. However, this transformation is not uniform across all galaxies. Observations reveal that some galaxies experience a relatively smooth transition, while others undergo episodic phases of activity and quiescence. These differences are often influenced by factors such as the galaxy's mass, the composition of its interstellar medium, and the presence of external perturbations like minor mergers or interactions with neighboring galaxies. The transition from an active quasar to a passive galaxy is also accompanied by profound changes in the galaxy's morphology. Many galaxies that host quasars start as irregular or highly disturbed systems due to the gravitational chaos of mergers. Over time, as the quasar activity subsides and the galaxy stabilizes, it often takes on a more regular shape, such as an elliptical or lenticular form. This morphological transformation is a key indicator of the galaxy's evolution, providing clues about its past interactions and the processes that shaped it. Another fascinating aspect of this transition is the interplay between quasar-driven winds and the chemical evolution of the galaxy. The outflows generated during the quasar phase are often rich in heavy elements, which are the byproducts of stellar nucleosynthesis. When these outflows mix with the galaxy's interstellar medium, they enrich it with metals, influencing the composition of future generations of stars. This process, known as chemical feedback, ensures that the galaxy's stellar population becomes increasingly complex over time, with stars exhibiting a broader range of metallicities. The eventual quiescence of a galaxy also affects its role within the larger cosmic web. Passive galaxies, with their reduced rates of star formation and diminished interactions with their surroundings, contribute to the overall aging of the universe. As more galaxies transition into this state, the universe's energy dynamics shift, leading to a gradual decline in the overall rate of star formation. This cosmic aging process is reflected in the universe's observable history, with younger epochs dominated by bright, active galaxies and older epochs characterized by quieter, more settled systems. Understanding these transitions also provides insights into the dark matter halos that surround galaxies. Dark matter plays a critical role in the life cycle of galaxies, influencing their structure, rotation, and interactions with other systems. During the quasar phase, the intense activity at the galaxy's center can create ripples in the surrounding dark matter halo, altering its density profile. These changes, while subtle, can have long-term effects on the galaxy's stability and its interactions with neighboring systems. By studying these interactions, astronomers can glean valuable information about the elusive properties of dark matter. Furthermore, the evolution of quasars into passive galaxies has implications for our understanding of galaxy clusters and superclusters. Quasars are often found in the densest regions of the universe, where galaxy interactions are most frequent. As these quasars transition into passive galaxies, they contribute to the buildup of massive galaxy clusters, which serve as the largest gravitationally bound structures in the cosmos. These clusters, in turn, influence the distribution of matter and energy on a cosmic scale, shaping the universe's large-scale structure. Modern observations, aided by advanced simulations, have begun to reveal the intricate details of these transitions. Computational models allow researchers to simulate the life cycle of galaxies, from their initial formation to their eventual quiescence. These simulations incorporate a wide range of physical processes, including gravity, hydrodynamics, and feedback mechanisms, providing a comprehensive view of galactic evolution. By comparing these models with observational data, astronomers can refine their understanding of the factors that drive the transformation of quasars into passive galaxies. As we continue to explore these processes, new questions arise. For instance, what determines the length of a galaxy's quasar phase? Why do some galaxies experience multiple active phases while others do not? And how do the properties of a galaxy's supermassive black hole influence its long-term evolution? Answering these questions requires not only more detailed observations but also a deeper theoretical understanding of the complex interplay between the various forces at work. Ultimately, the study of quasars and their evolution into passive galaxies is a testament to the dynamic and interconnected nature of the universe. It reveals how even the most violent and energetic phenomena contribute to the growth and stabilization of the cosmos, creating the conditions for new structures and processes to emerge. By unraveling the mysteries of these transitions, we gain not only a deeper appreciation of the universe's complexity, but also a greater understanding of our own place within it. The study of how quasars evolve into passive galaxies is a vivid reminder of the interconnected processes that drive the cosmos. It's a cosmic dance between chaos and order, energy and equilibrium. As the remnants of quasar activity fade, they leave behind galaxies that have matured into quiet hubs of stellar and planetary activity. However, the lingering effects of their tumultuous past are etched into the very fabric of these galaxies, visible in their structure, chemical composition, and even their interaction with surrounding space. The transition of a galaxy from a quasar phase is not just about the activity at its center. It's also about the galaxy's surroundings and how external factors contribute to its transformation. For instance, the gravitational pull from neighboring galaxies or the presence of an intergalactic medium can significantly influence the pace at which a galaxy settles into passivity. In dense galaxy clusters, where interactions and collisions are common, the environment may fuel bursts of star formation or reignite dormant black holes, creating a more episodic transition. On the other hand, isolated galaxies may quietly slip into passivity without external disturbances. The role of mergers in this process cannot be understated. Many quasars are thought to be triggered by galactic mergers, events that funnel vast amounts of gas into the central regions of a galaxy, igniting the quasar phase. However, as the merger completes and the dust settles, the galaxy may begin to stabilize, with its central black hole consuming the last remnants of infalling material. This marks the end of the quasar phase and the start of the galaxy's quieter, more stable existence. Interestingly, the remnants of such mergers often linger in the form of tidal streams or peculiar stellar distributions, serving as cosmic fingerprints of a galaxy's tumultuous history. During this transformation, the balance between cooling and heating within the galaxy becomes crucial. The energy output of the quasar phase heats the surrounding gas, preventing it from cooling and collapsing into new stars. This process, often referred to as feedback, is essential for regulating star formation and maintaining a galaxy's long-term stability. Without it, galaxies could overproduce stars, depleting their gas reserves too quickly and becoming inactive prematurely. Feedback mechanisms, therefore, act as a cosmic thermostat, ensuring that galaxies evolve at a sustainable pace. Quasars also play a pivotal role in shaping the intergalactic medium. Their intense radiation and powerful jets can ionize gas hundreds of thousands of light-years away, creating vast regions of heated plasma. These ionized bubbles, often referred to as quasar proximity zones, serve as markers of a quasar's influence, and can provide valuable insights into the conditions of the early universe. As quasars transition into passive galaxies, their influence on the intergalactic medium diminishes, but the imprints they leave behind continue to shape the cosmic web. Another intriguing aspect of this transformation is the role of dark matter. Galaxies are enveloped in halos of dark matter, which provide the gravitational framework for their formation and evolution. During the quasar phase, the energy released can redistribute dark matter within the halo, altering its density and structure. These changes can have long-term effects on the galaxy's evolution, influencing its rotation curve and its ability to retain gas. By studying these effects, astronomers hope to gain a deeper understanding of the elusive nature of dark matter and its interaction with visible matter. The eventual quiescence of a galaxy marks a new chapter in its life. Without the intense radiation and outflows of the quasar phase, the galaxy settles into a more stable state, characterized by slow, steady star formation or, in some cases, complete dormancy. These passive galaxies often exhibit a reddish hue, indicative of older stellar populations. Unlike their quasar-hosting counterparts, which are often chaotic and irregular, passive galaxies tend to have well-defined shapes, such as the smooth ellipses of elliptical galaxies or the subtle disk structures of lenticular systems. Despite their relative inactivity, passive galaxies are far from stagnant. Over billions of years, their stars continue to evolve, with some ending their lives in spectacular supernova explosions. These explosions not only enrich the galaxy with heavy elements but also contribute to its ongoing chemical evolution. Additionally, interactions with nearby galaxies, such as tidal stripping or minor mergers, can reignite brief periods of activity, creating a dynamic interplay between dormancy and renewal. The study of these transformations has been greatly advanced by modern observational tools. Telescopes like the Hubble Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, have provided unprecedented views of galaxies at various stages of their evolution. By observing distant quasars, astronomers can peer into the universe's past, witnessing the processes that shaped galaxies billions of years ago. Meanwhile, detailed studies of nearby passive galaxies offer a glimpse into the end stages of this transformation, allowing scientists to piece together a comprehensive picture of galactic evolution. One of the most exciting frontiers in this field is the study of intermediate systems, galaxies that are neither fully active nor fully passive. These transitional systems, often referred to as green valley galaxies, occupy a unique position in the evolutionary timeline. By studying their properties, such as their star formation rates and central black hole activity, astronomers can gain valuable insights into the mechanisms that drive the transition from quasar to passive galaxy. These intermediate systems act as cosmic laboratories, providing a real-time view of the processes at work. As our understanding of these transitions deepens, it also raises questions about the broader implications for the universe's evolution. The shift from active to passive galaxies represents a fundamental change in the universe's energy balance, with implications for everything from the distribution of matter to the rate of star formation. By studying these processes, we gain not only a better understanding of individual galaxies but also a clearer picture of the universe as a whole. The story of quasars evolving into passive galaxies is a testament to the universe's complexity and interconnectedness. It's a narrative of transformation, driven by the interplay of gravity, radiation, and matter. By unraveling this story, we not only illuminate the mysteries of cosmic evolution but also deepen our appreciation for the forces that shape our universe. As galaxies transition from their quasar phase into their quieter, passive states, they encapsulate the story of cosmic evolution, how the universe moves from high-energy phenomena to a more balanced and tranquil state. This metamorphosis is not simply a fading of activity, it's a complex and multilayered process involving intricate dynamics of star formation, gas depletion, and black hole quiescence, all interwoven with the surrounding cosmic environment. One of the most captivating elements of this transformation is how the energy output from quasars influences the galaxy's ability to form stars. During the quasar phase, the central black hole consumes vast amounts of gas, releasing energy in the form of radiation, winds, and jets. This energy, often referred to as quasar feedback, heats the surrounding gas, preventing it from cooling and collapsing into new stars. Over time, this feedback can drive out significant portions of the galaxy's gas, effectively shutting down star formation. This process, known as quenching, is key to the galaxy's transition to a passive state. The exact mechanisms of quasar feedback are still an area of active research. Observations reveal that the outflows generated by quasars can reach speeds of thousands of kilometers per second, creating massive, energetic winds that sweep through the galaxy. These winds can strip gas from the galaxy's core, ejecting it into intergalactic space. In some cases, this material can later cool and fall back into the galaxy, potentially reigniting star formation. However, in many instances, the gas is expelled entirely, leaving the galaxy with little fuel for future star formation. While feedback is a primary driver of the transition from active to passive phases, other factors also contribute. The depletion of gas reserves over time is inevitable as star formation gradually consumes available material. Additionally, interactions with neighboring galaxies can further strip gas, especially in dense environments like galaxy clusters. In these regions, galaxies experience a process known as ram pressure stripping, where the pressure of the intracluster medium removes gas as the galaxy moves through it. Together, these processes ensure that galaxies transitioning out of their quasar phase have minimal resources left for new star formation. The cessation of star formation has profound effects on the galaxy's appearance and characteristics. Galaxies emerging from the quasar phase often exhibit remnants of their turbulent past, such as disturbed stellar distributions, peculiar shapes, or residual gas flows. Over time, these features fade as the galaxy stabilizes, leaving behind a more uniform and structured system. Passive galaxies are typically dominated by older, redder stars, giving them a distinctive hue compared to the blue, star-forming galaxies. Interestingly, not all quasars follow the same evolutionary path. While many transition smoothly into passive galaxies, others may experience episodic bursts of activity, driven by additional mergers or the accretion of new material. These galaxies challenge the notion of a linear evolutionary sequence, suggesting that the transition from active to passive states is not always straightforward. Such complexities highlight the diverse and dynamic nature of galaxy evolution. One of the most intriguing aspects of this transition is the role of dark matter halos. These halos, composed of an invisible form of matter, provide the gravitational framework for galaxies and play a crucial role in their formation and evolution. During the quasar phase, the intense energy output can redistribute dark matter within the halo, altering its density profile. These changes can have long-term effects on the galaxy's rotation curves and its ability to retain or expel gas. By studying these interactions, astronomers hope to uncover new insights into the mysterious properties of dark matter. Another critical factor in the quasar to passive galaxy transition is the large-scale environment. Galaxies in dense regions, such as clusters, are more likely to evolve into passive systems than those in isolated environments. This correlation is due to the increased likelihood of interactions and gas stripping in crowded regions, which accelerates the quenching process. Understanding how environment shapes galaxy evolution is a key area of research, providing valuable context for the broader narrative of cosmic history. Advances in technology have revolutionized our ability to study these transitions. Observatories like the James Webb Space Telescope, JWST, and the Sloan Digital Sky Survey, SDSS, have provided unprecedented data on galaxies at various stages of their evolution. By combining observations across different wavelengths, from X-rays to radio waves, astronomers can build comprehensive models of how galaxies evolve over time. These studies not only reveal the life cycle of individual galaxies but also shed light on the larger structures that govern the universe, such as galaxy clusters and the cosmic web. The discovery of intermediate systems, or green valley galaxies, has further enriched our understanding of the transition from active to passive states. These galaxies occupy a unique position between the blue, star-forming population and the red, passive population. They provide a snapshot of galaxies in the midst of transformation, offering valuable clues about the processes driving this change. By studying their properties, such as their star formation rates, gas content, and black hole activity, astronomers can piece together the sequence of events that lead to quiescence. Quasars themselves remain enigmatic, despite decades of study. Their immense luminosity, powered by supermassive black holes, represents one of the most extreme phenomena in the universe. Yet, their eventual decline into passive galaxies reminds us that even the most energetic systems are subject to the passage of time and the laws of physics. This transformation underscores the interconnectedness of cosmic processes, where the life cycle of a galaxy is shaped by a delicate interplay of internal dynamics and external influences. The eventual quieting of a quasar is not the end of a galaxy's story but rather the beginning of a new chapter. Passive galaxies, though less dramatic, are still dynamic systems, with ongoing stellar evolution and interactions shaping their structure and composition. Over billions of years, these galaxies will continue to evolve, influenced by their environment and the remnants of their energetic past. This ongoing evolution highlights the universe's capacity for change, even in its most tranquil states. The study of how quasars evolve into passive galaxies is a profound reminder of the universe's complexity and beauty. It's a story of transformation, driven by forces that operate on scales both immense and intricate. By unraveling this narrative, we not only deepen our understanding of the cosmos but also gain a greater appreciation for the processes that have shaped our own place in it. Each quasar, each passive galaxy, is a testament to the universe's capacity for both chaos and harmony, a reflection of its ever-changing nature. As we continue to explore the fascinating transformation from quasars to passive galaxies, it's important to consider the long-term effects of this evolution on the broader cosmic landscape. The transition from active to passive states can have far-reaching implications for the structure and distribution of galaxies in the universe. For instance, the depletion of gas and the cessation of star formation in passive galaxies contribute to the overall shift in the cosmic star formation rate over time. This shift is especially notable when we look at the history of the universe. Early in the cosmos' existence, star formation was at its peak. The universe was filled with dense clouds of gas, constantly collapsing and forming new stars. But as galaxies evolved, especially in denser environments, this rate of star formation began to slow down. Quasars, with their intense radiation and feedback mechanisms, played a crucial role in this slowdown. The result was a gradual shift from a universe filled with young, star-forming galaxies to one dominated by older, passive systems. But it's not just the galaxies themselves that are changing. The surrounding intergalactic medium, the vast expanse of space between galaxies, also undergoes shifts in response to the changing energy dynamics of quasars. The intense radiation from a quasar can ionize the surrounding gas, heating it to millions of degrees and stripping it of its ability to condense into new stars. This process, known as the reionization epoch, marked one of the most significant changes in the early universe. Quasars were key players in this event, and their feedback mechanisms continue to influence the cooling and condensation of intergalactic gas. Interestingly, the shift from active to passive galaxies also raises important questions about the long-term fate of these galaxies. In their quiescent state, these galaxies are not entirely inert. They may still undergo internal evolution through processes like minor star formation episodes or mergers with smaller galaxies. Over time, however, the lack of new star formation means that their stellar populations age, gradually turning redder and dimmer. This aging process contributes to the growing population of red and dead galaxies, which will dominate the distant future of the universe. Another intriguing aspect of this transition is the role that black holes play in the evolution of passive galaxies. Quasars are powered by supermassive black holes, and these black holes continue to be present in the centers of galaxies after their quasar phase ends. However, after the quasar shuts down, the black hole's activity decreases significantly. Yet, even in their dormant state, these black holes can still influence their host galaxies. Some researchers have proposed that even quiet black holes might still be capable of minor outbursts or accretion events that could, in turn, influence the surrounding stars and gas. This raises the possibility that even though quasars may eventually fade away, their supermassive black holes might continue to play a significant role in the galaxy's evolution, though in a much subtler, more dormant way. The remnants of these black holes may continue to impact the surrounding regions by slowly accreting gas, emitting low-level radiation, or driving weak galactic winds. These quiet outbursts could subtly shape the surrounding environment and prevent galaxies from becoming entirely passive in the strictest sense. The study of supermassive black holes and their influence on galaxy evolution is an area of active research. Advances in technology, particularly in the realm of gravitational wave astronomy, have opened new possibilities for understanding the role these enigmatic objects play in the life cycle of galaxies. Gravitational wave detectors, such as LIGO and Virgo, are now able to detect the merger of supermassive black holes, providing insights into how these objects grow and evolve over cosmic time. These mergers are also thought to have an impact on the galaxies that host them, potentially triggering bursts of star formation or altering the galaxy's structure. Mergers themselves are a key factor in the evolution of passive galaxies. Many passive galaxies are the result of past mergers between two or more galaxies. These mergers can trigger a variety of events, from bursts of star formation to the formation of supermassive black holes in the center of the newly combined galaxy. However, over time, the merger process leads to the formation of a more stable, passive galaxy. The stars that formed during the merger eventually age and die, and the galaxy settles into a more passive state. It's essential to recognize that not all passive galaxies emerge from quasar activity. Some galaxies become passive without ever hosting a quasar phase. These galaxies may have experienced rapid gas depletion, perhaps due to interactions with their environment, or through the slow exhaustion of their internal gas reserves. In these cases, the transition to a passive state is less dramatic but still represents a shift from a high-energy, star-forming state to one characterized by aging stars and minimal new star formation. The study of passive galaxies is particularly important because these systems represent the end stage of galaxy evolution for many of the galaxies in the universe. Understanding how galaxies reach this passive phase, especially through the quasar-to-passive transition, helps astronomers better predict the future evolution of our own Milky Way. Our galaxy, though still actively forming stars, is expected to eventually reach a passive state after the available gas has been exhausted or expelled. This future scenario, though billions of years away, raises intriguing questions about the ultimate fate of our galaxy and the broader evolution of the universe. Passive galaxies are not just curiosities of the distant past. They hold the key to understanding the future of galaxies like our own. By studying these systems, astronomers gain insights into the processes that govern galaxy formation and evolution. These insights, in turn, inform models of the universe's long-term fate, helping us predict how galaxies will evolve as the cosmos ages. At the same time, the quieting of quasars into passive galaxies reminds us of the cyclical nature of the universe. The birth, evolution, and death of galaxies is a process that unfolds over vast periods of time, shaped by the interplay of gravitational forces, radiation, and the complex dynamics of dark matter. As we continue to study quasars, black holes, and galaxies, we deepen our understanding of the universe's most fundamental processes, uncovering the hidden mechanisms that drive the evolution of cosmic structures on the largest scales. As we continue to explore the fascinating evolution of quasars into passive galaxies, it becomes clear that the role of quasars and their associated supermassive black holes in the broader cosmic landscape is far more profound than simply marking an active phase in a galaxy's life. They are key players in the cosmic evolution of the universe itself. Their radiative feedback and the mechanisms that drive their transitions influence not just the galaxies they inhabit but also the intergalactic medium, the large-scale structure of the cosmos, and the very dynamics of cosmic expansion. One of the most significant aspects of the transition from active to passive galaxies is the role of quasar-driven winds and their impact on the surrounding intergalactic medium. Quasars are known to emit powerful winds of gas, primarily driven by the intense radiation emanating from the accretion disk of the supermassive black hole at their center. These winds can be incredibly energetic, moving at speeds approaching a significant fraction of the speed of light. The energy from these winds can push gas and dust out of the galaxy, effectively stripping the galaxy of its star-forming fuel. This process, often referred to as feedback, is a crucial mechanism that regulates the rate of star formation in galaxies. In fact, quasar-driven feedback is thought to be one of the primary factors behind the suppression of star formation in mature galaxies. By expelling large amounts of gas from the galaxy, quasars prevent the gas from cooling and condensing into new stars. This results in a shift from an active, star-forming phase to a passive, quiet one. As the galaxy runs out of fresh gas, it is no longer able to form new stars at the same rate, and its stellar population slowly ages. This process is not instantaneous. The transition from an active quasar to a passive galaxy can take billions of years, and the mechanisms that drive it are complex. The exact timeline of quasar evolution depends on various factors, including the mass of the supermassive black hole, the availability of gas in the galaxy, and the rate at which the galaxy interacts with its environment. In some cases, galaxies may undergo multiple episodes of quasar activity and feedback before they finally settle into a passive state. As quasars transition into passive galaxies, they leave behind a fascinating legacy. The supermassive black holes at their centers, now dormant, remain as enigmatic remnants of the once active phase of the galaxy. These black holes continue to play a subtle role in the galaxy's evolution, even in their quiet state. They may continue to accrete gas from the surrounding environment, albeit at a much slower rate than during the quasar phase. This slow accumulation of matter may generate weak radiation or even trigger faint, low-level activity in the black hole. In some cases, the gravitational influence of the black hole may cause the stars in the galaxy to move in unusual ways, leading to complex patterns of motion that provide clues about the history of the galaxy. The remnants of quasars can also be seen in the galaxy's structure. Many passive galaxies exhibit unusual features, such as the presence of a central bulge or a stellar halo, which can be the result of past interactions or mergers with other galaxies. These interactions may have triggered bursts of star formation or the growth of the supermassive black hole. Even as the galaxy transitions into a passive state, the scars of these past events remain etched into its structure. Furthermore, the study of passive galaxies and their transformation from quasars is not just an exercise in cosmic history. It has practical implications for our understanding of galaxy formation and evolution. By observing these galaxies and the processes that drive their transition, astronomers can refine their models of galaxy evolution and make predictions about the future of our own Milky Way. The Milky Way, while still actively forming stars, is on its way toward becoming a passive galaxy in the distant future. This is because, eventually, the gas needed to form new stars will be depleted or expelled. Our own supermassive black hole, Sagittarius A*, is already a dormant black hole, though it has not yet reached the point where it will significantly affect the galaxy's star formation. Understanding how quasars evolve into passive galaxies can help us predict what will happen to the Milky Way as it ages, and how the cessation of star formation will affect its structure and dynamics. In addition to providing insights into the future of our galaxy, studying the transition from quasars to passive galaxies helps us understand the broader processes that govern the evolution of the universe. Quasars and the galaxies that host them are not isolated phenomena. They are part of a larger cosmic narrative that includes the formation of galaxies, the growth of supermassive black holes, and the evolution of the intergalactic medium. By studying the life cycle of quasars, we gain a deeper understanding of the forces that shape the universe over cosmic timescales. The cosmic landscape is constantly evolving. Just as quasars once dominated the universe with their intense energy and activity, the universe is now moving toward a future where passive galaxies will become the norm. This transition is not just a story of the death of a cosmic phenomenon. It is a reflection of the universe's ever-changing nature. As galaxies evolve, so too does the universe itself, shifting from a time of rapid star formation and quasar activity to a future where galaxies become quieter, older, and more passive. The transition from quasars to passive galaxies is a cosmic process that spans billions of years, but it is a key chapter in the story of the universe. By understanding this transformation, we can learn more about the forces that drive galaxy evolution and gain valuable insights into the future of the cosmos. The quieting of quasars marks the end of an era, but it is also the beginning of a new phase in the life of the universe. As we continue to study these fascinating cosmic objects, we are not just observing the past, we are unlocking the mysteries of the future. In the farthest reaches of the universe, where quasars are still being born, the cycle of galaxy evolution continues. As we look deeper into space, we may observe galaxies at different stages in their life cycles, some still in the throes of quasar activity, others slowly transitioning into their quiet, passive phase. These observations are not just about understanding the present but also about looking into the future of the universe. The transformation of quasars into passive galaxies is a story that will continue to unfold over billions of years, and in studying it, we are gaining valuable knowledge about the cosmic processes that shape the universe and its ultimate fate. The quiet galaxies of the distant future will be a testament to the power of quasars and the dramatic influence they had on the evolution of the cosmos. From their fiery, energetic beginnings to their eventual cooling and fading into passivity, quasars have shaped the galaxies they inhabit and left an indelible mark on the universe itself. As we peer into the vast expanse of space, we are reminded that even in their quietest moments, galaxies and their supermassive black holes continue to tell the story of the universe. One that is still unfolding, one that is still full of mysteries waiting to be uncovered. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.